In this video, we'll see about the conversion of the continuous AWGN channel noise into a vector channel. That is, we want to convert the continuous AWGN noise into the discrete representation, which is suitable for the digital communication system analysis and simulation. So here, the additive white Gaussian noise channel model, it is a fundamental model in communication theory, and this will represent a channel where the primary impairment to the transmitted signal is the addition of random noise. Okay, so here this noise, it is characterized by two key parameters or the points. The first is the additive noise. So here the noise, this additive noise, it is simply added to the channel or the signal. Okay, so here the additive noise, it is the noise which is being added to the signal, and the white noise, it has a flat power spectral density across all the frequencies of the interest, and here this means that the noise power, it is evenly distributed across the frequency spectrum. Okay, so in white noise there will be even distribution of the power, that is the noise power, across all the frequency spectrum. And this Gaussian noise, here the noise samples follow a Gaussian or normal distribution, and this distribution, it is completely defined by the mean and the variance, where the mean, it is assumed to be 0 and the variance will represent the noise power. So this is about the additive wise Gaussian noise channel model. Now we'll see how to convert this. Suppose here we have the received signal, which is represented by x of t is equal to si of t plus w of t. We'll take this as equation number 1, where x of t, it is the noisy signal which is received at the receiver, and w of t, it is a sample function of the white Gaussian noise process. Now, if we consider, so here x of t is noisy signal at the receiver, w of t is a sample function of the white Gaussian noise process, and if we consider the output of the correlator, which will be a random variable, and it can be defined by this equation. So xj is a random variable which is given by integration 0 to t, capital T, x of t, phi j of t dt. So this can be written as xj is equal to sij plus wj. We'll take this as equation number 2, where the value of j, it varies from 1, 2 up to capital N. Now here sij, it is given by integration 0 to t sj of t phi j of t dt. We'll take this as equation number 3. So here sij, it is the deterministic component of xj, and this is due to the transmitted signal si of t. Okay, this is due to the transmitted signal si of t. Then next we have wij, which is given by the equation integration 0 to capital T w of t phi j of t dt. We'll take this as equation number 4, where wij, okay, this should be wij, it is the sample value of the random variable wj due to the noise, that is w of t. W of t is what? W of t is our sample function of the white Gaussian noise process. Now, let us consider a new process which is given by x dash of t is equal to x of t minus summation j is equal to 1 to n xj phi j of t. So we'll take this as equation number 5. Now what we'll do is we'll substitute equation 1 and 2 in 5. This was our equation number 1 and this was our equation number 2. We'll substitute these two equations in this equation number 5 and see what we'll get. So x dash of t as it is, x of t is what? It is si of t w of t here, minus summation j is equal to 1 to n, xj is what? It is sij plus wj into phi j of t as it is. So now when you simplify this, you get x dash of t is equal to w of t minus summation j is equal to 1 to n wj into phi j of t. So here minus summation j is equal to 1 to n Sij into phi j of t will be Si of t. So this plus Si of t and minus Si of t gets cancelled, and we get only W of t minus summation j is equal to 1 to n here Wj into phi j of t, and we'll take this as equation number 6. Now this equation number 6, it is similar to equation number 5. Okay, so here you can see you have x dash of t and x dash of t. Here it is x of t, w of t minus sign, then you have summation xj, wj, phi j of t and phi j of t. So equation 5 and 6 are similar. So we can write from these two equations that x dash of t is equal to w dash of t. Okay, so now we will use equation number 4 in equation number 5. So our equation number 4 was this. We'll use this equation here in equation number 5, and we will get the received signal as x of t is equal to summation j is equal to 1 to n xj into phi j of t plus x dash of t. So this equation, it can be written as, here you can write it as x of t is equal to summation j is equal to 1 to n xj into phi j of t plus, as we have got here x dash of t is equal to w dash of t. So we can replace this x dash of t by w dash of t. So this is our equation number 7. Now this equation number 7, it is the random process, because of which the channel noise, this is the random process, and this is because of the channel noise and the receiver input. Okay, so this was about the conversion of continuous AWGN channel into a vector channel.